Okay, so today's lesson is on moments, and we're not talking about short periods in time that kind of make you think of wistful memories in the summer looking at butterflies. What we're thinking about are turning forces about a pivot. Okay, so a turning force around a pivot is called a moment, which seems weird. In maybe year 9, you might have just called it literally a turning force, okay? But we are going to have to call it a moment, okay? And there's lots of situations in which these are important, none more so than a seesaw, okay? So you can see here we've got a pivot, and here we've got a turning force. This guy would be going down, and the turning force would be this way. Now we need to know whether turning forces are clockwise or anti-clockwise. So this would be anti. And this one, okay, because that would be the seesaw. If this guy jumped off, yeah, if we just lose him, dead, then this would be clockwise, okay, because that's the way it would move if this person either lost weight or was removed. Okay, it would move clockwise. Okay, now when it's balanced, okay, when clockwise anti-clockwise moments balance, okay, there's no movement. Okay, so in this case, if these people were equal and are equal distances from the pivot, then the anti-clockwise and the clockwise moment would be equal. Oh yeah, that's a better diagram. Okay, so what you can do then to change the size of your moment is to either change your weight, which is quite hard, or you can change your position. So I'll come to the equation in a moment, but the further you are from the pivot, the bigger your turning force. And you probably know that if you think about, I don't know, trying to balance on a seesaw. If you wanted, if there was someone much larger than you, you'd move further away, okay, and that would increase your moment, the size of your moment, okay. So the formula, all right, is force. So that could be weight, for example, times the distance from the pivot. Okay, that's got to be from the pivot. And force in newtons, distance is in meters, so moments are measured in something called Newton meters. Okay, really straightforward. N times M and M. And the key thing is this. This is in a balanced situation, by the way. The sum of all the clockwise moments equals the sum of all the anti-clockwise moments when it's balanced. Okay, so when it's in a state of equilibrium. Okay, and this is the principle of moments. So if we have a look at an example, all right, we've got two weights, W1 and W2, and two distances from a pivot, D1 and D2. And what we've got to do is calculate W1. Okay, so this is what we want to know. If W2 equals 4 newtons, so I'll write that in. D1 equals 0.25 meters. Notice we're working in meters, so centimeters. If you had centimeters, you'd have to convert to meters. And D2 equals 0.20 meters. Completely out of scale diagram. Okay, so we work with what we've got. All right, so the weight or the force times the distance of, again, assuming this is balanced, weight times the force of this side, okay, this side here, equals the weight times, the weight times the distance of that side there, equals the weight times the distance of this side here. Okay, so we can work out that side. Okay, but what we'd probably want to do is get this on its own. So because it's times here, get rid of it and we make it divide here. Okay, so the weight of this object here equals the weight of the second object times the distance of the second object divided by the distance of the first object. So we'd get this 4 times 2, 4 times 0.2, that should be meters, okay, divided by 0.25 meters, and the weight would equal 3.2 newtons, okay, and we can just double check that makes sense, okay. This one, ignore the diagram, this one is slightly closer than this one, okay, so if it's balanced we would expect this to weigh slightly less than W1. So W2 would weigh slightly less than W1, and if we have a look at our answer, that's the case. So we can say, right, that's probably a right answer. Okay, so if we have a look at a past exam paper question, alright, we've got a gardener here using a steel bar to lever a tree stump out of the ground. I did this recently, it's quite hard. I should have used the principle of moments. What I was doing, I was here, this is me. Okay, and I was just using my spade like that, okay. He's made himself further away, so he's therefore increased the turning force, increased the moment, and that's helped, okay. So it says, when the gardener pushes with a force of 3 newtons, the tree stump just begins to move. Calculate the moment produced by the gardener on a steel bar. The problem with this question is it's giving you two distances. It's giving you 0.8, which is the horizontal distance, and 1.2, okay. Just have a think for a moment which you would use, okay, and we use the actual distance along there, okay. The horizontal distance is rather irrelevant, okay, so this would be 1.2 times 300, which equals, what would that be? I don't know, 360, yeah, 360, something like that. 0.2 of, yeah, I think it'd be 360. Okay, I'm just working it out in my head. So that would be 360 Newton meters. If I'm wrong, send an answer on a postcard to me. This one was much harder. This was quite a recent one. Okay, because it looks like you've got both objects on one side of the pivot, and you have, but you need to look carefully at it. So a student wants to weigh himself, but the only balance available is a Newton meter that measures up to 200 newtons. Yeah, obviously the student is living in a different world to us. The diagram shows how the student solves the problem using moments. I mean, he spent all this time, he probably should just go to his mate's house and get another balance, but he hasn't. So the first thing to do with any problem like this, okay, is to figure out where your clockwise and where your anti-clockwise moments are, okay. Now this is a situation in balance, okay, because obviously he's measuring himself. So what we do is we find the clockwise moment. So here's the weight of the person, alright. So if this is removed, this part, okay, then he will move this way. So this would be an anti-clockwise moment. If we then look over here, okay, we've got this rope that's kind of like in a state of equilibrium, state of balance, okay, and again, because it's been pulled on by this support, if he was removed, this man was removed, the turning force would be this way, the moment would be this way, okay, so this would be clockwise. So we've identified where our clockwise and our anti-clockwise moments are. So then what you'd do, okay, is you'd work out your clockwise moment, okay, which we know, and our anti-clockwise, which we don't know. So our clockwise one would be 160 newtons times 1.75. 1.75 because it's the force of it is 160 newtons, okay, and the distance from the pivot is 1.75 meters. So we have 1.75 times 160, our anti-clockwise one, our distance would be 0.5. As you can see here, we've got 0.5 meters from the pivot, and we'd have to times that by the weight of the person, which we don't know. So we do weight equals 1.75 times 160, and then we divide it by 0.5. So we've got 0.5 there, we want to get it down here, so we do 0.5, okay, and that should equal so that equals 560. Okay, now key thing, we're talking about the weight of the person, okay, so we include the units newtons. Alright, and we can just check if that makes sense. So we know there are 10 newtons in a kilogram, roughly. So this person weighs 56 kilograms, and that seems a sensible answer. He's not weighing something ridiculous. Okay, so 56 kilograms might be around about 9 stone. Okay, so it makes sense. It's a sensible answer, and that's what you've constantly got to do. You've constantly got to check your answers.